Hello and welcome back to Introduction to Astronomy. In our previous segment, we talked about two different ways of bending a wave. And so one was reflection, when the wave bounces off of something. And then the other one was refraction, which was going to be the bending of a wave when it's going through something. And now we want to talk about a third way of bending a wave, which is going to be called diffraction, and that's going to be the bending of a wave when it goes around an obstacle. So an example of this that you're familiar with is if you've got a room, and then here's the door to the room, and then let's say that you're out here and you're talking, and then somebody is inside the room. If you speak loud enough, they can hear you, even though the sound waves are, if the sound waves are not going directly to the person, the sound waves are going this way, and then they're bending and going into the person like that. Now, on the other hand, if you take a flashlight and you shine a flashlight at the door, you notice that it goes in a straight line. So what's the difference between the two situations? In one situation, the wave is bending as it's going around the obstacle. In this case, it's the door. But in the other case, light doesn't bend much when it goes through the door. It goes in a straight line. So what's the difference between these two situations? Okay, so I want you to go to the internet and then go to PhET, and then type in PhET wave interference. So you're going to go to that simulation. Are you there? Okay. So once you get there and you open up the simulation, click on the thing down there at the bottom that says slits. So we want to look at how a wave interacts with a slit. Okay, have you got that open? All right, so now you got a bunch of sliders, so you can change the wavelength of the wave, you can change the size of the slit, and also you can change the number of slits, but we just want one. So when you get on there, change it so that you've just got one slit that the wave is traveling through. And we're going to be interested in what happens to the wave when it goes through the slit as you change the wavelength of the wave and as you change the diameter of the slit or the size of the slit. So do that. So first, keep the size of the slit the same, but change the wavelength and see how that changes the bending. And so what you should be looking for is, there's the slit, here's some waves that are coming in like this, and so the distance from this line to that line is going to be the wavelength, because this represents a crest, and then this represents a crest, and then in between is the trough of the wave. So the distance between a crest and a crest is the wavelength. And what you're looking for is when it goes through the slit, notice it's doing this. It's bending around it. So it's not just going straight through. So in the case up here, if it went straight through and did not bend, that would be like light. But in this case, it is bending, and so it's going over here, just like you can hear, and it's going out through the door and then is opening up. So what do you notice? Well, what you should notice is that as you increase the wavelength, that is going to increase the amount of diffraction, the amount of bending. So try that. So increase the wavelength and see what effect it has when it goes through the door. And then what I want you to do is, now this time you're going to keep the wavelength the same, but you're going to change the size of the door, the width of the door. And you should notice that the closer the door gets, so the smaller the opening, the more it diffracts. And the greater the opening, the less it diffracts. So how could we state this mathematically? Okay, you notice equation 8.4. So the angle that it spreads out, that's going to be theta. So that's going to be that circle that has the bar through it. So that's called theta. And so that's going to be the angle that it opens up. And it's going to be proportional to the wavelength. Notice where the wavelength is. It's on the top. So what does that mean? If you increase the wavelength, it increases the bending of the wave. Okay, then diameter is on the bottom. Diameter is going to be the opening. So how big is the opening? So if we make the opening big and the diameter is in the bottom part of a fraction, then what comes out is small. So it doesn't bend very much. So the larger the opening, the less it tends to bend when it goes through. So now let's compare sound and light. So sound has a large wavelength in comparison to the size of a door, so it bends, sound bends when it goes through a door. Light waves, on the other hand, have a very small wavelength, so they don't notice the door. It's like they don't feel the door, and they just go straight on through, and they don't bend much. Now, we can bend visible light. It's just that we need a really, really small door in order to do it. So you can actually do this. So take your fingers, okay? Take your fingers, hold them up to the light, and slowly bring your fingers closer and closer together. And what you'll notice is just before your fingers touch, it will get black in between your fingers. So try it. Do it. Okay? So did you notice? So what's going on is as the light is trying to squeeze in between your fingers, it's interfering with itself and is causing destructive interference, so it turns black in between your fingers. So that's an example of diffraction in action, so to speak. All right, so who cares? Why are we interested in the process of diffraction? Well, we'll see that in the next segment.